Welcome students. We are back with another lesson. In this lesson, we'll start a new chapter, atoms and nuclei. So, in this chapter, we'll first discuss Thompson's model of an atom. So, in the year 1899 or 1898, J.J. Thomson proposed that atom is a sphere of positively charged matter with electrons. This negative blue circles, can you see? These are your electrons. These electrons are embedded in it. The positive charge is uniformly distributed over the entire atom. Fine. The positive charge is maintained throughout the atom. The arrangement of the electrons inside the continuous positive charge is in such a manner that it balances the positive charge. That means the positive charge of this body of atom is balanced by the negative charge of this electron. Hence, these two make each other electrically neutral. So, to give a clear picture, your Thomson said your atom look like a watermelon, where this the fruit part, the red part is your positive charge, whereas the seeds, as you can see, they are uniformly distributed and these are negatively charged electrons, right? And he also said it is quite similar to your pudding. So in this pudding, this whole body is positive charge and the small fruit and nuts you see, they are your negative charge. So his model was also called as. Now, on the basis of his model, Thomson could explain some processes like chemical reaction, the radioactive disintegration, and some observed spectra of elements. Fine. This spectra of elements we will see in the forthcoming lessons. Okay, we will discuss about it in more details in our upcoming lessons. For now, you can understand it like this. Let us say when there is an atom, you supply some energy to the atom, and if you have a diffractor plate, okay, this is your diffractor plate. What happens if you give sufficient energy to this atom? The electrons are ejected, isn't it? If you give energy to the atoms, the electrons at the ground state becomes highly energetic and they jump out of the electron or jump to a higher shell. Now, in the process, when they jump to a higher shell, what happened? They radiate some energy. Fine. Those radiation we measure in terms of various spectra. Okay. It's like suppose you are watching this on some machine. Okay. Whenever there is a jump or there is a transition of electron or electrons are ejected, what happens? You see a peak. Fine. If there is lower transition, then lower peak. If there is a higher transition, higher peak. Fine. So these are your spectra of atoms. Different atoms have different spectra. Okay, we will discuss it in more details in our upcoming lessons. Fine. Now, according to the Thompson's model, he could explain the spectra of elements. Fine. There were failures with this model also. It could not explain the origin of several spectral series in the case of hydrogen and other atoms. Fine. We will discuss about the spectral series of hydrogen atom in the upcoming lessons. Fine. Now, it fails to explain the large angle scattering of alpha particle in Rutherford's experiment. It couldn't explain the scattering or angle scattering, or why does your alpha particles get scattered in your Rutherford. So, what was this alpha particle scattering experiment? So, in the year 1911, one of the physicists, Ernest Rutherford, along with his two associates, H. Geiger and E. Marsden, performed this alpha. So, let us first understand what is a alpha particle. To understand alpha particle, let us take a helium atom. Now, this is the nucleus of the helium atom. And how many electrons does helium atom has on its outermost shell? 2. Fine. Now, let us remove one electron. If one electron is removed, then it gains a positive charge. Let's remove the other electron also. So if the other electron also is removed, then it gains one more positive charge. Fine. So alpha particle is nothing but the nucleus of a helium atom, where this atom has lost two of its electron and gained two positive charge. An alpha particle is a helium ion, that is a helium atom from which two electrons have been removed. It has a charge of equal to plus 2e, and its mass is nearly 4 times the mass of the proton. So let us understand the construction of the alpha particle scattering experiment, or let us understand the experimental arrangement. Now, in this case, a radioactive source, okay, this is your radioactive source. It can be your radium or it can be your bismuth, okay, any radioactive element. Fine. This element is enclosed in a thick lead block with a very narrow opening. Okay. Now, the alpha particle or the radioactive particle emits the alpha particle. This alpha particle are collimated into a narrow beam through a narrow slit. Or I'll say this alpha particles, okay, let us say it is giving out many alpha particles. Those alpha particles are being focused like a laser, okay, collimated. In this case, I'll say collimated. To make them pass, you can understand like it is passing like a laser. Fine. They are made to pass in a narrow beam through a narrow slit. Fine. This beam falls on a thick gold foil. Okay, as you can see here, this is your alpha particle beam. It goes and falls on a thin gold foil. Okay, it is very thin. It is of the order of 10 to the power minus 7 meter. Now, as your alpha particles fall on this gold foil, the alpha particles get scattered, as you can see in this figure. Right? Now, to observe the scattered alpha particle, what the Rutherford had did is that they had either put a fluorescent screen, that means every time an energy particle strikes on the screen, a light glows, or more specifically, they have covered this one with a zinc sulfide screen. Fine. Now, outside the zinc sulfide screen, they have placed a microscope to observe this phenomenon. Fine. Now, in this way, the number of the alpha particles scattered at different angles can be counted. Fine. This whole experimental apparatus is enclosed in a evacuated chamber to avoid the scattering of this alpha particle with the air molecules. Fine. So let us discuss few of the observations which they have made. Now, most of the alpha particle pass straight through the gold foil, as they have observed that most of the alpha particles, can you see this straight line? They could pass undeviated. Okay, they does not undergoes any deviation. That means there's no change in the angle. The angle this with which they were coming, they are going out on the same angle. Okay, there's no change in the direction. So I'll say most of them, most of the alpha particle pass undeviated. Okay, now some of the alpha particles got deviated, or they got a small deflection, as you can see in the figure. Like very few, not all of them, some of them got deviated. Fine. A very few of the alpha particle, about 1 in 8,000, gets reflected through 90° or more. Now, lesser number of alpha particle as compared to the previous one got scattered at an angle which turned out to be more than 90°. Now, occasionally, okay, occasionally, this is very rare, an alpha particle got rebounded from the gold foil, suffering a deflection of nearly 180 degrees. Okay, so on very rare cases, okay, it's like out of large number of this alpha particles scattered, very like one or two alpha particle, it came in this direction and returned back in the same direction. They underwent a deflection of nearly. So let us discuss some significant results they have derived from this experiment. Now, as most of the alpha particles pass straight through the foil, so most of the space within the atom must be empty. As we have seen, like most of the alpha particles pass undeviated. That means there must be a very large space inside the atom as compared to its constituents. Fine. To explain the large angle scattering of alpha particles, they first suggested that all the positive charge and the mass of the atom is concentrated in a very small region called the nucleus of the atom. Now, as we have seen that some of the alpha particles underwent scattering, some of them underwent small scattering, some of them underwent large angle scattering. Okay, now to explain this large angle scattering, they have suggested that the entire, or let us say the positive charge, okay, the positive charge, or I'll say the mass of the atom, they have suggested that the positive charge or the mass of the atom, this mass of the atom which is positive in charge, is concentrated in a very small region at the center, which is known as the nucleus of the atom. Fine. Now they have seen if the small mass which is concentrated at the center is nucleus, which is positive in charge, then there must be a negative charge also, because atoms are electrically neutral. So the nucleus is surrounded by a cloud of electrons whose total negative charge is equal to that of positive charge of the nucleus. So the atom as a whole is electrically neutral. Fine. Now finally, the scattering of the alpha particle is due to the Coulomb's repulsion between the positive charge alpha particle and the positive charge nuclei. Now, why is the scattering of alpha particle taking place? It is because of the Coulomb's electrostatic force of repulsion, which we have studied in our electrostatics. Now, why they are being repelled? Repelled. It is because the alpha particles are also positively charged. The nuclei are also positive charged. So the two positive charge repel. Now, in this experiment, we will discuss some two important points. Fine. First important point is the distance of the closest approach. Suppose an alpha particle of mass m and initial velocity v moves directly towards the center of the nucleus. It experiences a Coulombic repulsion and its kinetic energy gets progressively converted into its electrical energy. Now let us consider your alpha particle, this red dot, this laser pointer. Let us assume this is a alpha particle. Now this is undergoing a head-on collision with the nucleus of this atom. Fine. Now, as the nucleus of the atom is positively charged, so as the alpha particle. So what do you observe is, as the alpha particle slowly approaches towards the center of the nucleus, what happens? All of its kinetic energy, in the kinetic energy due to its motion, is being converted into a electrical energy, which results into a repulsion of this alpha particle, hence results moving or hence causing it to move in backwards opposite direction. Fine. Now, at a certain distance r naught from the nucleus of the alpha particle, stops for a moment and then begins to retrace its path, that is it is scattered through an angle of 180 degrees. So what happens is, as the alpha particle slowly approaches the nucleus, it moves to a certain distance where its motion becomes almost zero, or there is no motion. The velocity almost becomes zero. The alpha particles then move backwards. Now, this point at which your alpha particles motion becomes completely nil. Okay, so we will measure this distance. As you can see, this distance is denoted as r naught, and this distance is called as the distance of the closest approach. How close the alpha particle can get to the nucleus of this atom. Fine. Now, the distance of the closest approach can be written as twice of k. What is this k? K is your force constant, 1 by 4 pi epsilon naught. Fine. Times Ze. Ze is the charge of the nucleus. Okay. Here E denotes the charge of the individual nucleus and Z denotes the number of the positive nucleons or particles inside the nucleus, and this E denotes the individual charge divided by your kinetic energy of the alpha particle. Fine. So I can simplify and write it as 4kZe square by mv square. Fine. Your k alpha equals to half mv square. The 2 goes up. So you have 4kZe square by mv square. Fine. Now, the next important point which we'll discuss is your impact parameter. The impact parameter is defined as the perpendicular distance of the velocity vector of the alpha particle from the center of the nucleus when it is far away from the atom. Fine. Now, as you notice, let us assume this red dot as your alpha particle. As your alpha particle slowly moves towards the nucleus, what happens? It undergoes deflection by an angle of theta. So here, let us consider the direction in which it is moving. Let us consider to be at like your velocity vector of this alpha particle. This is the velocity vector of the alpha particle. Fine. Now, this is the velocity vector of the alpha particle. Now, draw a perpendicular line to the velocity vector. Can you see this B? This is the perpendicular line drawn from the velocity vector of the alpha particle to the center of the nucleus. This dashed line is the center of the nucleus. So the impact parameter denotes this small distance when your alpha particle is far away from your nucleus. Fine. So why this impact parameter is important? Now this impact parameter, it gives us the idea about how much impact this alpha particle will undergo due to its motion and its positive charge. Fine. Or I can say it like this. Your impact parameter help us to determine following points. Okay. Like if I'll say for large impact parameter. Okay. If I consider this distance to be large. If I consider the impact parameter to be large. Okay. Now let us consider the direction of the alpha particle. Now, in case if your alpha particle is very large, what happens? The alpha particle which is moving far away from the nucleus, will it undergo any deviation? It will go a small deviation, but not as much as compared to the one which has a small impact parameter. So can you see how much important is your impact parameter? It basically gives us the trajectory of the scattered alpha particle. Okay. The larger the alpha impact parameter, it will pass undeviated. The smaller the impact, fine. So based on the observations and the results which we have discussed so far, on the base of this, Rutherford proposed his model of the atom. Now, according to his model, an atom consists of small and massive central core in which the entire positive charge and almost whole mass of the atom are concentrated. The core is called the nucleus. Now, according to the Rutherford, whole positive charge and the mass of the atom is concentrated at the center, this black part. This is the nucleus of the atom. Right, and all of the mass lies on this nucleus. Right, this outer shell or this red dots, they do not contribute anything to the mass. The mass contribution or the weight to the atom is coming only due to its nucleus. The size of the nucleus is very small as compared to the size of the atom. Right, as you can see, the size of the nucleus turns around to be somewhere around 10 to the power minus 15 meter, whereas the size of the atom is 10 to the power minus 10 meter. So it is very small as compared to the size of the atom. Right. Third point, the nucleus is surrounded by a suitable number of electrons so that the total negative charge is equal to the positive charge on the nucleus and the atom as whole is electrically neutral. Now, the charge distribution, like suppose say the positive charge of this nucleus is this is the positive charge of the nucleus, and the negative charge is such well distributed like this red dots. They represent your electrons which are negatively charged. They are so well distributed that all of the concentration, or I'll say all of this, results into a electrically neutral atom. Okay, your atom is neither too much positive, neither it is too negative. It is neutral, stable. Fine. And final point, the electrons revolve around the nucleus in a various orbit just as the planet revolves around the sun. So according to your Rutherford, he proposed that electrons revolve around the atom in a planetary mode. Now, apart from his results and his achievements, there were some limitations of Rutherford's atomic model. Now let us discuss those limitations. Okay, according to the electromagnetic theory, An accelerated charged particle must radiate electromagnetic energy and the electron revolving around the nucleus under continuous acceleration towards the center. Okay, now according to your electromagnetic theory, if a charge revolves around the nucleus, it should radiate some energy. Okay, it should give out some energy. Fine. Now, if this charge which revolves around the nucleus and if it gives energy, will it be able to maintain this position? No. So what will happen? This electron revolving around the nucleus will slowly undergo a continuous acceleration towards the center. That means it should continuously lose energy and move in an orbit gradually decreasing radii. The electron should follow a spiral path and finally it should collapse into the nucleus. So what does it say? That as it radiates energy, it should slowly move towards the center of the nucleus and collapse. But is our atoms collapsing? No, our atom is stable. So Rutherford's atomic model cannot explain this point. Fine. Coming to the next point, in Rutherford's model, electron can revolve in orbit of all possible radius. So it should emit a continuous spectrum. But an atom like hydrogen always emit a discrete spectrum. So according to Rutherford's model, he said that the electron revolves in a planetary motion, but he hasn't specified in which shell or in which energy level your electron is revolving. For according to his model, the atom or the electron which is revolving around this second orbit, it is possible for the electron to that same electron to go and jump to the 32th level of this, or let us say this level which has an energy 32. This the fourth energy level. Okay, the electron, it is possible for this electron which is in the first energy level to move to the fourth energy level. Okay, but is it possible? No. So because of this failure, he cannot explain the hydrogen discrete line spectrum. Okay, so what is this discrete line spectrum? So when a electron, let us say, which is in this second energy level, okay, when this electron, it makes a transition from the second energy level to your first energy level. As you can see in this case, what happens? It radiates some energy. Fine, it radiates some energy. Now when an electron makes a transition from this energy level to this energy level, it radiates some more energy, but the energy will be different as compared to your first case. So when you obtain this on a screen, this looks like something like this. Okay, so this is the spectrum of the hydrogen atom. So your Rutherford's model cannot explain this spectrum of the hydrogen atom. Okay, the spectrum of the hydrogen atom we will discuss. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain.